to systems. Well, they used to not have me teach this lesson. This actually was just like a, let's brush up on what you know about systems, and then we like moved into learning matrices. And we have found that students are understanding the matrices and where they come from, and they also don't appreciate them. And so I think that's another reason. Thank you. I think that's another reason they have added this lesson, is to have a better understanding of systems, because some people don't. I don't know if it's a change in like when we teach stuff, but kids are coming to my M1050 class less prepared to do systems of equations. And so I think that's why 1050 added this lesson. Well, this was added, I didn't have guided notes to it and whatever, and so I had to hurry and throw together some things because it just was recently added. And so that's why it's only 2 pages, but it's also only 2 pages because they rarely assess on this alone. I would consider this a setup lesson, because matrices is your actual topic they care that you know how to do, but students are understanding matrices as well without this as a prerequisite to it. So it's a short lesson because I'm like, you know what, let's just make sure we understand systems, and really they're going to assess your own matrices. This is, I doubt you'll see just a general systems question on the test. I highly doubt it. They might do a true or false, I guess, but I mean, they ask systems questions. I shouldn't say that. They ask questions like theoretical questions about systems, but like the long solving, it'll probably be a matrix, okay? So that's what today is about, is kind of like your setup. It's like a setup to what you guys will be learning. And so matrices are solving systems. And matrices are used to organize, because when stuff is left as an equation, it gets a little bit messy and the variables kind of get in the way. And then when you have 3 variables and 3 systems, it's just kind of a mess. And you're going to see it today. And after we do one long 3x3 matrix or 3x3 system, you're going to be so grateful for matrices after this lesson, because you're going to be like, oh yeah, this is awful. It's not awful on the 2 variables, okay? But it is awful on the 3. And so we're going to do it. You guys have to have, when you have 2 unknown variables, you have to have 2 equations. That's what makes it a system. If you have 3 unknown variables, you have to have 3 equations for it to work out. So whatever the number of unknown you have to have that number of equations to kind of solve it. All right, so let's just review. How many of you feel like you remember systems? Raise your hand if you do, or give me the gauge. Give me just your gauge. You remember systems a little bit. You've heard the word systems even. Okay? How many of you feel like back when you learned how to solve systems with substitution and elimination, it went well? Like you remember it, you remember substitution, you remember elimination. I'm just kind of getting a gauge. Anything helps. Those of you who are fun haters, I need your feedback. Okay, so you're a fun hater. So a system is a set of equations that involves the same variables. So x's and y, like if I have to find x and y and you have another equation, it also should have x's and y's, same variables, okay? You can't have like x, y, and then just another one like a z, okay? So you need to have it, they match some variables. A system of linear equations is a system of equations in which each equation is linear, and a solution to a system is an assignment of those values for the variables that make the system true, meaning you take it, you plug it in. We all know what solutions are. You take them, you can plug them in. Well, it has to be true for each system or equation. So you take your solution and it should plug it in, and if you plug it in, 2 should equal 2. 5 should equal 5. Like it should work out on both, okay? So that's what a solution to a system is. So in order to solve it, you find all the solutions to the system to each equation. All right, I've reminded or refreshed your memory on your guys' methods you've learned in the past. Let's go through those methods, okay? You guys will get to pick substitution or elimination. You're going to even use these methods when we go to solving nonlinear systems as well. These are going to be linear. What does linear mean? What's the degree on all the variables? Yeah, the variables should have just a degree 1. That's what makes them linear. And so when they're linear, it's a line and another line intersect each other, right? And that's what makes them linear. So the solution is that intersection. If you guys remember when you did it graphically, which today we are going to kind of like use graphs and intersections to predict it. But back when you guys learned systems, it was one of your methods. but it's kind of a tedious method because you have to be really organized. And if you don't have a grid paper to do it on, it's not fun. It's not fun to sit there and like try to find where the solutions align, right? And so it's actually not the most efficient method. And so we're not going to officially go over it, but we are going to include it in our check. And your guys' homework makes you practice with it. So your homework will make you like refresh your memory on what a system means, okay? So, okay, substitution method. We are going to solve for a variable, and we're gonna start with a two variable equation, and then you're gonna take it and you're gonna substitute it in. Substitute the variable you found in step 1 into the other equation, and at that point, everything should be in terms of one variable. So again, if I solve for y, I take it and I'm gonna substitute it in for my y, and so everything should be in terms of x. So then, you guys are going to be able to solve for x in that one you just substituted into. You take it, and it's called back substituting. You back substitute into the first equation that you had found in step 1. And then you don't forget to write your answers as ordered pairs, because these are technically solutions to the system. And so the system, like what is true for this line and is true for this line is technically an intersection. And so it's an ordered pair. So you guys will write it as an ordered pair. Okay, we're going to do that method first, and then we're going to circle back to elimination. To make things easy, I literally only have 2 2x2s and then 1 3x3 because that takes us long enough, okay? And I feel like that's good enough practice. I know normally we give you extra problems to practice, but I feel like they're not going to assess you on just this topic. I think we just got to hurry and refresh our memories. That's what it is, a refresher. Okay? All right, let's do substitution first. I don't know if I left myself enough room. I was trying to keep the notes short, but... All right, substitution is first. So let's actually I'm going to check with our graph first, actually. Let's do that. So let's check with our graph and kind of predict and make a prediction or like try to find a solution if possible. How do you think we would sketch these on a graph? What's the easiest way to graph, if it can be? Solve for what? Y. Y is the easiest to solve for. So if I rearrange this one, I'm going to solve for y. And so by solving for y, what would I do with the 2x? Yeah, simply minus my 2x, and that would be a 2x plus 5, negative 2x plus 5. So where do I graph? My y-intercept is at 5, and then what's my slope? Down to over 1, right? And we may have to continue this to be able to find out where the intersection is. It's going to be a little bit ugly because I don't have this on grid paper or anything. Now, we can graph the other one by solving for y. I actually think this is a little tedious to solve for y. Is there another method of graphing you guys learned for linear functions when it was in standard form, maybe? Do you guys remember at all finding maybe the intercepts of the plug in a 0 for your x, plug in a 0 for your y, and that'll give you your intercepts quickly? Because I feel like this is a little uglier to solve for y, which you can still solve for y. There's potentially going to be fractions though, because I'm noticing as I go to divide numbers over, my y-intercept is not going to be a whole number, okay? So sometimes I'll just say, all right, let's plug in a 0 for x. So I'm going to cover it up, pretend there's a 0 there, and what do I get when I solve for y? Divide by 6 and get what? Negative 1/3. So this one is actually not a great one to kind of like get the actual answer. And that was my mistake because I just kind of threw these examples in from a book, not forgetting that I wanted to check graphically as well. So that's my fault, but I'll switch that for next year. But let's go ahead and plug in a 0 for my y, and let's divide by negative 4. What do you guys get? 1 what? 1/2. So it looks like I have a y-intercept at about 1/3, and that does not hardly help me at all. And then it looks like I have an x-intercept at a 1/2, which is not awesome. So it looks like our solution, if we had the time, the one on your guys' homework is going to be nicer. You guys have an actual grid. You guys are going to actually have ones that are like y equals, a little bit prettier to solve. But we're predicting our solution being like down in that quadrant, right? Yeah.
The y negative 1/3.
Oh yeah, thank you. That changes things, Nora. But so this is a way to make little predictions of where it would be, and like I said, your homework is a little nicer to you than I just put on here. I kind of recently added that I wanted to check with graphically, so that's the graphic way. So there's a good chance that this is gonna be like 2 something, right? Maybe like 2-1 or pretty close to there, right? Now on your guys' homework, you'll be able to like follow it and actually get those coordinates. Okay, so there's our prediction. There's gonna be our prediction to our solution. Okay, let's go ahead and actually solve it using substitution first. So which variable looks the easiest to solve for in either equation? I usually pick the easiest one with less division. If I can avoid dividing, I can avoid fractions. So that's what I try to do. The top one, which we had technically already solved for. So we technically already solved for y, so let's just continue with that. And I usually circle the variable I solved for in my step 1 so that I know which one to take it back to when I back substitute. Okay. So next, what would I do with the y? So we already used this equation, so what do I have to do now? Take it and what? I plug it in to the other equation. Because if y equals something, you can use that y anywhere you see y, okay, besides plugging it back into itself. So we're going to take negative 4x plus 6y is equal to negative 2. In place for my y, I substitute. That's why this one is called substitution. Is this coming back to anybody? Good. I know we don't focus on systems in Math 3, so it's probably feeling a little bit like it's been a minute, right, for some of us. So negative 4x minus 12x plus 30 is equal to negative 2. What does that simplify to? So 16, negative 16. Do you guys care if I minus the 30 over right now? And then are we all on the same page? Negative 16. Nora, when I have candy back and I restock it, I forget you get a treat for catching things. I love when you guys are always like listening. I would rather people catch stuff than just go with it. You guys, I just found an answer. Now we can accidentally move on at this point. Some people tend to move on, and remember, systems have to be ordered pairs. So you haven't finished your system. You just found one part of it. What do I now do now that I have found that variable when I did the substitution? Oh, sorry, that's the wrong one I'm pointing at. I went back and I solved for that variable, and now we do what? Back substitute, because you're like, oh, well, y equals this. So we're going to take it and back substitute. I'm going to use yellow. So I take this and I go right there, right in for that one. So I get to say negative 2 times by 2, and then a plus 5 is at negative 4 plus 5, which is at 1. So I just found my y to be at 1. So what would I say my solution is? Is that positive 1, 2, 1? Is that what we kind of predicted with our sketch once Nora caught me? Yeah, that looks like it's at about 2, 1. Had I been able to do my upright up one, my rise over run, I would have found that point. Okay. Now that is substitution, and I think to kill 2 birds with 1 stone, we can either do elimination on this one or substitution and elimination on both. Which one should we do so we can work on it twice? Should we do it for both? Who thinks they want to see everything twice? Okay, if you guys don't mind, let's do elimination here. Does that work? And then that way we have plenty of time to do the awful 3 by 3. Cool? All right, let's do it. Let's start again. So let's start with a sketch just to have our prediction. Again, I don't know if I picked a good one to do the sketch, but when I was reviewing your homework, I was like, oh gosh, their homework makes them sketch or do the graphs or like see solutions with a graph. Okay, so let's go ahead and solve for y. It looks like I might get fractions, so we'll kind of see. So 2y, we get a negative. Nope, we don't get fractions. That's good. I'm going to minus my 3x over and then divide everything by 2. So when I divide everything by 2, there's my rise over run. But luckily 14 is divisible by 2, and what do I get? Do you guys agree that it's 7? Okay, so right here I'm going to go up 7. And then my slope is what? It needs to be negative, right? So down 3, so we're now here at 4, and then over 2. Everybody good with that one? Okay, let's do the other one. I'm going to do the other one in a different color. So that was this graph. Let's do this other one I'm going to add a 2y actually, and I'm going to minus the 2. Are you guys okay that I rearranged it the way I did? I added the 2y, and then I chose to minus my 2. And then when I divide everything by 2, this turns out nice. It's a 1/2 x, and then a minus what? Good. This one's a little easier to track it. So I'm down here at -1. And then I was able to go up 1 over 2. Yeah? Let's continue. Up 1 over, up 1 and over 2. Let's see if this one's correct. We're going to go down 3 and over 2. So where does it look like my solution is going to be?
4-1.
Looks like my solution is going to be a 4-1. Now, is everything always easy to graph, and is it going to be easy on a 3x3 because those ones are like 3-dimensional? So those ones we won't be using the graphing method. So you can't always use the graphing method because some people might be like, well, I'm going to graph every time if that's how easy it is. And it's not, so we need to know all the methods. Okay? Let's go ahead and do this. So we know where our answer is, but let's just show it using elimination now. I just wanted some space below it, so I'm going to write elimination right here. Okay, elimination. Who remembers what elimination is? I have the steps up above, but who wants to put it in their own words?
You make it so that so you have your two equations and you make one of them have the same factor, but one's negative, and then the other one it would be positive.
Good, same coefficient. Yep. You want to make it so that you can cancel one. You can when you add functions, because you are allowed to add equations to manipulate things and kind of decide to narrow it down, I guess. But you can manipulate an equation until two match so that you can cancel. Okay. So what happens is we are trying to essentially get rid of the variable so we know what that. Because you guys can't solve an equation when there's two variables. You can't. You have to get them in terms of one. So adjust the coefficient. You take a coefficient, and you have to do this by multiplying one or more equations with the appropriate number so that you pick one to eliminate. Okay? From there, add equations, and after you guys add the equations, you will solve for the variable that you got everything in terms of. Okay? After you solve for that variable, you're back-to-back substituting. This is a nice part. With elimination, it doesn't matter which equation I take and put it back into. Not with elimination. So you can pick any equation to go back and put it. Okay, let's do it. Okay, so elimination is my favorite actually. If I can eliminate, I do it. I hate substitution with a passion. I don't know why, but I do. So elimination is my favorite. So if you guys can get good at it. And elimination is actually our matrices. So what we do with matrices is elimination. Okay, we just organize it in a matrix. So this is the one I really want you guys to get good at, but at least understand when you get to matrices. All right, now if we look at this, I didn't do a good job of picking a good example, but you'll see it on the 3x3 in a minute. I would normally think, okay, if I want to eliminate my x's, I would have to times this by a negative 3x so that they eliminate. But what's already nicely set up for you? The y's are already opposites, and they're the same coefficient. So I don't have to manipulate anything. I can just go straight to adding. But if I wanted to eliminate the x's, we would have times everything by a negative 3. Okay, you guys remember this? So let's go ahead and go to the next step by adding these equations. When I add them, what do I get? Do you guys remember you get 4x? And then what happened here? They canceled, and so it looks like we're here. And then what do we get for our x? It's a 4. Perfect. This is where I take this and I can back substitute it in whatever I want. So I think this one's the easiest because it's all by itself. So I'm going to take it and substitute it into that one. Okay? So I'm going to say 4 minus 2y equals 2. And then I'm just going to go ahead and solve for y. And it looks like when I divide by a negative 2, did you guys all get a 1? There we go. Now, how do I know I'm right? I kind of skipped it, but I have more space here. How do I know that really is a solution to my system? To both of them, right? So you guys can take it back and you guys can check, and I can plug in a 4. So I get 12 plus 2 times 1 is 14, so it works with that one. And then I can plug this in and say 4 minus 2 times 1 is 2, should be a 2. And they both check out, so it works in the system. I know that we're going to get a little lazy on the homework when we do stuff, so I don't expect you guys to check every single thing, but if it comes down to their exam and you have the time, I would always check it. I had a problem on one time when I was grading a system that they were solving. It was a matrix though, and one student made a silly mistake. It was literally just a negative. And I was like, they did the whole thing right, oh no. And they only got points for setting up the matrix. But luckily, the director at the time let us do 4 points for the proper setup, which was crazy to me. But I didn't get the person any other points, 4 out of 10. And I was like, that's just so sad because they knew how to do matrices and do row elimination so well. And I'm like, how do I not give them even partial points? This was my director's answer to me. My director said to me, they had the choice to check their answer, and they didn't. And so they deserve to miss 6. That's kind of what I was told. So just keep that in your mind. Like if you don't take something and check it, you probably, you didn't take the time to do it, and so you probably deserve missing those points. So just keep that in mind, okay? I didn't agree completely because that student showed so many. So they've changed the rubric slightly. I think they now give you some points for the proper setup in the matrices. And they actually now added to the rubric, at least they did last spring, and it said the person, they showed correct row operations. I think they were allowed 1 or 2 points for like some correct row operations, even if they messed up, there was some correct row operations. So I think that I was able to fudge a few more points after and got like 5 for some kids or 6. All right, you guys, this one is the worst. It's so awful. I'm just preparing you. It's pretty awful. We might do substitution. I do think it's important to, no, we're not going to do substitution. It's really bad. But you can do substitution, okay? Substitution is pretty awful because look at what happens when you try to solve for a variable. It's not in terms of 1, right? So you essentially have to like substitute it in and then take that and then solve. So like we would take this and substitute it, and now things are in terms of y's and z's. And then you would maybe take that and potentially solve for a different variable, and then you would take it and substitute it, and then you'd also substitute this x here and find, and that y would have to, anyway, would have to go into that one. So you essentially have to solve for a variable, substitute, solve for another variable, substitute. You essentially have to substitute like 3 separate times before you can even have it. But your job is to eliminate down until you have 1 variable. Does that make sense? If anybody wants to see a 3x3, we can, but I don't think we need to. We're actually trying to assess you on matrices in a minute. So I'm going to do elimination. But that's what substitute would take, is solve, substitute, and it's awful. Okay? So I'm just going to make a note that we would substitute like 3 times. All right, let's do elimination. Okay, let's do it. So elimination, I forgot to add to the steps just because, like I said, I was trying to keep the notes quick. You have to eliminate twice. So this one takes, you eliminate twice in order to get it down to 1 variable. Okay? Okay, let's do it. Is there a variable you guys like the best to try to eliminate? Z looks like it's nice maybe with this equation.
Yeah.
Because one's positive and one's negative. I like that, Taylor. Let's do that. So how would I manipulate it? What do you see?
I would just multiply the first one by 2.
Good. It looks like I can multiply everything by 2. It has to be both sides of an equation to keep it balanced. So this would become 2x. This would become what? 2y. Good. Now this one I get to just straight rewrite it. Because it looks like but sometimes you have to multiply both of them. Like, what if the number was like, they both could multiply to a 12? You know what I mean? Like if I was trying to eliminate, for instance, these two, this one I times by maybe a 2, and this one I times by a -3. So sometimes you have to do both equations, right? But I get to just copy this one over, so that's awesome. Okay, so we're choosing to eliminate z's. What do I get once I eliminate and I go to add this? What do I get when I eliminate my z's? 6x minus 1y is equal to 14. Okay, now I now have two variables, but I do have to have two equations. So I have to somehow get another equation with x's and y's. So you would actually eliminate z's again and do two different equations. Does that make sense? Okay, so that's why you have to eliminate essentially twice. Because once you eliminate twice, that leads us to two equations with two variables. And now you're just doing a 2 by 2 if you can eliminate twice. So we've got to eliminate z's again. And so if we were to stick with z's, I could do these two, but then I would have to times both equations, which we could practice. Do you want to practice timing both equations? Or would you guys rather just do something to the top equation to eliminate? Okay, let's do it. I'm going to do that in blue. So if I want to now do those two equations and I'm picking my z's to eliminate, what would I have to times the top equation by? -3. It looks like a -3. Yep, you guys are right. Why did we pick negative, by the way? They do need to make one positive, yep, because the bottom one is negative, and we're not changing the bottom one. So we're going to go over here, and we're going to make this, Reef, if that gets loud, do you want to, you can shut that. Is that a plus 3z? And then luckily, I don't have to do anything to, oh, we're doing the wrong one, sorry. This one is coming over. So we get 2x minus 2y. If you're an organized person, you will do wonderfully on these. If you're not a very organized person, you need to make sure you're organized. Figure it out. Figure out a way to stay organized, label things like, where's this coming from? And it really helps me with partial points if I were a pretty organized person. If it's pretty ugly and I can't find what you're doing, it's partial points are really hard. Okay? All right, let's eliminate. What do we get?
-x minus 5.
Good. Good. Do you guys agree? Okay. Did I do something wrong? Yeah. Thank you. Sorry, we usually double check ourselves too. So let's see.
Like the.
So we're here. -3.
-1.
Oh, there we are.
Degrees.
Positive 3. Positive 3. There we are. Okay, let's do it again. So we're at the -x minus 5y is 8. See, in that little mistake, when we go to solve and then back check everything, we would have noticed, we got our variable wrong. Let's just retrace our steps. So we multiplied a -3 through. You guys are my 30 set of eyes, 37 set of eyes. We multiplied the 3 through. And then we carried over the 2x. And then we added. Is everybody in agreement that it looks good? Okay. Is there anybody who has any questions before we move on? We all good? All right. What do we do now? We technically eliminate 3 times. I said if you eliminate twice. And then from these two variables, you guys solve it. And if you're going to choose to use elimination, you would eliminate or substitute, right? So which one do you want to do with these two? Do you want to eliminate or do substitution? I heard eliminate first. Should we just do it? Okay. So let's bring it on over. I'm going to rewrite my 6x and my y over here. All right. I love when we have a coefficient of a 1 somewhere because it makes our lives a little easier. I think the x's are the easiest to eliminate. Do you guys agree? Since one's already negative. Okay. What would I times this by? Positive 6. So it looks like this becomes -6x minus 30y. Let's see, is that a 48? Okay. We're going to go ahead and eliminate. Bless you. and that gives me a negative 31y, 62, and then is that a negative 2 for y'all? Awesome. We have found a variable. Okay, that's a good thing that we finally got to a variable. So I take this and I just slowly work my way back. So I get to take this and put it into one of my 2x2s, my 2x2 variable system or linear system. 2 variables, two equations. So I think this one looks great because, well, it doesn't really matter. I think they're equally the same easy, easiness. So we're gonna go 6x minus my negative 2. And then what do you guys get? You got plus. And then did you guys get a 12?
Yeah.
And so we get to claim x is what? 2. Perfect. Now what? Yep, I go back to my 3's and it doesn't matter which one because we're using elimination. So I think the top looks the best. So we're going to take both of these and I'm going to take this top one and we're going to say, all right, 2 plus y, which I accidentally found y. Let's see. So my y is a negative 2 and then my z and then a negative 1. That cancels, so I get to say negative z is negative 1, which if I divide by negative tells me z is what? Good. How should you write this answer? It's an ordered triple. Yep. You should write them as ordered triples, x, y, z. This is a 3-dimensional plane. So a paper would, the fact that you guys write on a paper is an xy plane, right? X and y. And then this dimensional, the third dimensional thing that comes out is what makes that plane the third one, the z plane. Okay? And so you guys always write it in order. So this should be a 2, negative 2, and a 1 when you guys are done. And if we take the time to check them, we should check them in all equations. So when I take it and plug it in, I get to say 2 plus my negative 2 minus my 1 should be a negative 1, and it works, and it should work for all 3. Okay? Tedious, right? And if you guys feel like you don't like that, I'm hoping when you guys are shared the refresh on the matrices, I'm hoping that you guys love it. Okay? Here's an example of an XY Z plane that's kind of like broken, so sorry. These are broken. It's broken over the years, right? So that's the third dimensional plane. So here's the plane, here's X, and then there's your guys' normal Y, and the one that comes out turns into your guys' third dimension. So like wherever they intersect, it has to be on all 3 variables. So kind of interesting if you guys view them as planes, and we need to fix that actually so we can have it. All right. Okay, let's go to some specialty things and then we're done. Okay, I've just got the specialty. Your guys' word problems, your guys' homework has word problems. So I might help you set up one word, like how you would handle a word problem, 2, but I really want this to be my focus before I try that one, and then we'll see what time it is. All right, I ran out of time to actually write in an actual example, so you'll have to kind of forgive me there. You guys will run into linear systems in 3 different scenarios. Okay? Let's just do 2 by 2 because it's hard to draw a 3 by 3. Is that okay on a screen? I can't really draw it. So let's just do 2 by 2s. A system that has, you guys could have 3 different scenarios. You can have where 2 equations do overlap or do cross each other at some point, and so you guys will be given an ordered pair, or for a 3-dimensional situation, an ordered triple. And so you guys may run into having an actual solution that you get to take and check. Okay? What happens if I have a line and it happens to be maybe parallel to another line, and so they will never intersect? If something never intersects, what do you think is going to happen with that system? Lines that are parallel never intersect. If they never intersect, what do you think is going to happen with that system? It's, yep, no answer, no solution. The ones that are no solutions are considered inconsistent systems. So when this happens, you guys will notice like a variable will go away, or you'll get like something that is untrue. Like a number will never equal a different number, right? 0 won't ever equal a 2. So what will happen is when your variables, when you go to cancel things, this happens. And you can step back and be like, oh, if I had solved for y, I would have realized these were parallel. That's what you would have realized. Is if you guys had taken those equations and actually compared them, they would have had like matching matching slopes, essentially. You guys would have realized that on these ones. So they're considered inconsistent. Okay with that terminology? Okay. A system with infinitely many solutions is actually called dependent, and you actually don't get to, which I want to show you what this would look like. You don't get to actually say just infinitely many, because it's actually not just infinitely many. The variables are still dependent on each other. So what happens on these ones is the lines ended up coinciding with each other. Oh my gosh. Let's see if this will work for me. These lines essentially end up being the same line. So like if you were to solve for y, you would realize, oh, they're the same exact line. Or if you like divide, because it's hard to see if they're exact because sometimes things can be a multiple of each other. And if you aren't looking for it, it's easy to overlook, and I'll kind of show you in just a second. But these ones are considered an infinitely many solutions, but you will never say that. You guys will say that they are dependent. And dependent systems only has one variable that's infinitely many. So here's an example. You would say, oh, x and y are such that maybe x is an element of all reals, or y is, but y behaves like this. And it behaves like some sort of equation. So even though I could pick like anything for x, y would depend on x. It's not like x could be 2 and y could be 100 and whatever, and it's going to work. It actually isn't going to work. They're still dependent on each other. So like I will still be able to find infinitely many answers, but if I choose x to be 70, y behaves a certain way, or vice versa. Whatever one you make is your all reals. That little e is a symbol. E stands for like an element of. If you guys haven't seen that before. So x is an element of the all reals, and then this one is dependent, or vice versa. This could have been y is an element of all reals, and then x equals. Okay? I'll kind of show you what they kind of look like, and then we might run out of time to like, I wanted to do a word problem, but I would rather let you guys try to work sooner. But maybe we'll at least just talk it through assigning variables, okay? Your homework makes you guys do some. And maybe with your homework, you'll be fine. I have not seen them do a word problem in a while that has to make you set up a matrix, or set you up a system, but you never know. I want to still ask it because they tell us to teach it. Okay, here's an example of one. So let's go 2x. Actually, let's go 2x plus y equals 5. And then let's do 4x plus 2y equals 8. Okay? Let's just do elimination, since that's where we're leading to with matrices anyway. You have to know substitution for nonlinear systems. So it's not like substitution is like not a good method. You have to know it, but you'll see it again during nonlinear systems. All right, what variable do you guys want to eliminate? Yeah, let's do the y's. And so the easiest one that we all noticed is timesing the top by what? Good. A lot of us are seeing the same thing, but there isn't only one way. You guys can manipulate things a couple different ways. Okay, this turns into a negative 4x, a minus 2y, and then a negative 10. And then when we transfer this one over, you would have been like, oh. And maybe you aren't noticing it yet, you know? Hold on.
The bottom isn't negative.
Yeah, let's see, what did I just do?
It's not the bottom.
Oh, thank you. I was like, hold on a minute. That should have. So, if anybody's noticing, these are nearly identical when we did that, and they're all identical, just opposite signs. So what you're going to notice, in your attempt to just eliminate your y's, we actually also had eliminated the x's. So what this means is we get and if this has a number, we get an untrue statement. It does not equal -2. So what's going to happen is you'll notice all your variables go away and you get an untrue statement. Deal? And this one you get to say inconsistent. It's an inconsistent system, no solution. Okay? But let me show you a different setup. What would happen on this one? We would say 2x plus y equals 4. And then I want to do -6x minus 3y is equal to -12. And if you guys aren't looking for it, you'll overlook it. But can anybody see it right now? If we go to solve for y, just for practice, I want to show you. Will you guys solve for y with me? What do you get?
6x.
Right here, let's do this one. -2x plus 4. Do you see it? So when I go to solve for y here, I get -3y and then a +6x, and that 12 is still there. And then when I divide by a -3, I get a -2x plus 4. Look how they end up being identical. So if you do want to like check, you know, but if you guys can tell that they're essentially a multiple of each other on all the terms, then, and this one was a multiple of each other technically, if you look, if you times everything by 2, but this side wasn't. But if you notice the right side is as well, you can pick it out. But you still can't just say infinite many and walk away. Okay, so let me show you what happens. Let's go ahead and do elimination. What do you guys want to do?
3.
Let's do it. Let's times by 3. So let's do a 6x plus 3y, and that's equal to a 12. This one would be, and I'll tell you right now, the 3 by 3s are not near as easy to pick out. So the process is what you're going to start to solve with elimination, you guys, and then realize, oh, this is inconsistent. Like you're going to solve it like you're solving, assuming it is going to give you a solution. Oh, everything cancels, and we get 0 equals 0. So instead of saying infinitely many and walking away, make note, I have had kids deducted for not saying a dependent system. So you got to tell them that you know it's dependent. And then when students forget to write it as dependent, at least you get those points, okay? However, a dependent system, you still determine what it behaves like. So, on this one, we could write it one of two ways. 2 by 2s are the easiest. On 3 by 3s, I'll show you when we get to matrices how to do those ones a little bit better. But 2 by 2s are the easiest. You guys could write this one of two ways. You get to say, all right, x and y are such that if I chose my x to be an element of all reals, my y would behave like what? We already have a solve for. What does your y behave like? -2x plus 4. You literally write the equation in terms of the one that's all reals and just say x is all reals, here's y in terms of x, and that's how it should behave. Now what if I wanted to make y my element of all reals? What if I had said, hey, my y is an element of all reals. I need to know what x would behave like. So could I manipulate this and decide what x, or any of these, and decide what x would behave like? You can. So you can sit there and solve for whatever variable you want. So let's just take this and let's minus the 4 over and make this y minus 4 is -2x, and then divide by -2 and divide by -2. So what does x behave like? Do you guys see that it's a negative 1/2 y? And then a what? The 2 is under both of them. So what would you say? Negative 1/2 y, and then the 2 has to go under the 4 as well. What would you say? +2. Good, Brian. Yep, +2. Very good. So if you wanted that one to be your unknown, you would say 1/2y + 2. So either, you guys are welcome to write or, like these solution sets would be written this way. So this is a little bit of a bummer because you guys are used to being able to say infinitely many when it's just x equals, right? But when it's ordered pairs and ordered triples, it doesn't work that way. They're still dependent, and you can't just say any number exists. 270, nope. So if something's 2, then y has to behave based on 2. And so that's kind of why they're called dependent. Okay? I'm going to let it be and let you guys practice on your homework. I do want to hurry and at least show you what you would do if a system... I'll try to be quick. I apologize. I wanted this to be a fast lesson, but there's just more to it than you think. So if I have a story problem, and if I ever have 2 unknowns, I have to set up the 2 equations, okay? So I'm going to read off the story problem. I lost it in my book. Let me see if I can find it again. I want to read the story problem better, but I might have to just say it, what the gist of it is. And put things into words. I found it in my notes, and I was like, oh, I want to look back at that one. Okay. I'm not finding it. That's okay. I'm not finding the one I wanted to do. So I'll just read this off. Okay. Okay. All right. If I give you a quick story problem, let me hear you talk about it, okay? So I have tickets to somewhere, and I was able to sell, between my tickets, I was able to sell the regular price tickets. So I was able to sell regular price tickets and discounted tickets. And my total number of tickets was, I sold about 525, okay? So I sold about 525 tickets. But I also said in the story problem that the regular price tickets are going to be $10 tickets, and my discounted tickets were $8, and I was able to make $46.30 at the end. Okay? And so we want to know how many regulars we had sold and how many discounted we had sold. Does that make sense? So when you guys have 2 sets of these totals, and I need to know how many discounted and how many regulars there are, then I have a 2 variables, 2 equation type situation. Does anybody have any idea how I could potentially set up this system and then we would solve it? Which we're going to not solve it just because I want to get you guys working. But tell me how I could do this. Give me one equation you know. This is the number of tickets I sold. This is the money we sold at the end of the day. This is how many of those tickets are. My hint to you right now is let's establish what we could call X and what we could call Y. So let's name some stuff. What do you guys want to name them? What's that?
The regular X's.
Let's call that. Let's let X equals our regular tickets, and let's let Y equal our discounted tickets, like the number of them. How are you? Good. KJ, this is for you. So if X represents our regular and then the Y represents our discounted, give me one equation I can set up with X and Y. It's an easy one. It's the number of regulars and number of discounted. And those numbers represent the number of tickets, and this one represents the money. What's that?
X plus Y equals 500.
Good. Let's do an equation that deals with the number of tickets, okay? And that's an easy one. X plus Y would equal to 525 tickets, because this stands for how many I sold. I don't know how many of each, but I do know I sold 525. Let's just write that down. Well, I also know that I made $4,630. So can you think of another equation that deals with the money you made instead?
10x plus 10.
Good. At $10 for my regular price tickets, plus at $8 for my discounted tickets, that should equate to $46.30. And now, as soon as you have a system and two variables, you now know you're capable of solving it. Does that make sense how you might have to do some word problems? And so my hint to you is name things, name something X, name something Y, and then go from there. And you can kind of build your system that way, okay? And then we would have solved this. Okay, I'm going to be done because I feel like this has turned, you guys are good.